It's a device that we've been working on outside of class. It is an assistive device for the blind that takes pictures and is able to describe your surroundings with AI. We wanted to apply our E84 knowledge to create a circuit for it. We want to create a battery protection circuit that is able to limit the amount of current that flows from the battery into the device once the battery reaches a certain level of discharge. This is important because our 3.7 volt batteries, once they go below a certain threshold, usually 3.2 or 3 volts, they can start becoming permanently damaged. So we want to limit this as much as possible, conserving the battery health of our device and allowing the user to be able to charge their device without the battery becoming permanently damaged after extended hours of use. Okay, let's see how to build this circuit. Here we see the battery connected to the power rails. Red goes to power and black goes to ground. Then we see our IC connected at one pin to the battery, power, at another pin to ground. Then its output is connected at one node to the 4.7 mega ohm pull-up resistor, and this node is connected to the N-type MOSFET's gate. Then, backtracking a little bit, the IC, as mentioned before, will output a floating high or a floating low, which will be either pulled up or pulled down by this resistor. If it pulls high, then this will bring it up to the battery's voltage, since it's connected here. And if it pulls low, it'll just take it to ground. At the N-type MOSFET, one of the pins is grounded, which is the source. Its gate again is connected to the IC's output, and its drain is connected to a node with the second pull-up resistor, the 100K, and the gate of the P-type MOSFET. The source of the P-type MOSFET is connected to the battery through this wire, and then its drain is connected to our load, the 200 ohm resistor. Then this load is grounded back to the negative channel. For more on how this circuit actually works, and for simplicity and to avoid confusion, let's go to fault stat and see how current flows. Let's look at the case where the battery voltage is above that 3.3 threshold that we selected. Here, highlighted in blue, the node to the left is a representation of our IC's output pin. Since we are above the threshold, this pull-up resistor between our output pin and our battery will bring up the IC's output to the battery's voltage, in this case 3.5 volts. And this will allow for the gate voltage here to be greater than the source voltage, which will allow for current flow here and will bring this node to a lower value than the battery. This will allow current to flow freely through the P-type MOSFET, and this will mean that current flows normally from our battery into our load, or in our case, the device. In this next case, we represented the IC's output pin as a ground because now, as you can see on the top left, the battery is now below our threshold voltage of 3.3. Although it looks like it's static, there is a little bit of current flowing, although it is very, very little. That's why it looks so slow. Compared to the previous case, where I'll remove this real quick so you can see how much current flows, where there were 13.66 milliamps of current. Now our MOSFETs limit this to only 203 nanoamps, which is a very, very big decrease, and this will allow for our battery to be protected once it is discharged over a certain point. Now Now we have connected the discharge battery, and without having changed absolutely anything about the circuit, now being in the microamps setting, we see we have basically 0 current flowing through our load, which means that this circuit works. If you want to check, we can simply replace the battery, replace the wires. We can do it all in one take, so it looks and feels believable. We connect ground, we connect here, and now going back to milliamps, we see we have 19.48 milliamps.